Hi folks, welcome back. I hope you're all doing well. Today I want to take a look at a paper that was published just about a month ago at EuroSys 2022. And this paper asks a really interesting question. We've seen lots of mechanisms for virtualization and isolation with techniques like hypervisors and virtual machines, but their granularity has always been somewhat coarse-grained. They usually virtualize or isolate an entire program or a process. The question this paper is asking is, what if you could push that granularity all the way down to a single function? And why would this be useful? We've seen several kinds of applications recently that use functions as the unit of execution. The most prominent example of this is the rise of serverless applications, but there are also other established use cases such as user-defined functions in databases, or just simply calling a third-party library that you don't completely trust. Those use cases are currently served by existing mechanisms like containers, but particularly in the case of serverless functions, they suffer from some disadvantages, things like cold start latency, for example. The fundamental problem is that mechanisms like containers were not meant for such fine-grained isolation. They were meant for isolation at the level of an entire program or an entire process. The authors in this paper are introducing a new abstraction that they call Virtines, that is designed for isolation at the function call granularity and leverages hardware capabilities already present for virtualization. Before getting into the design and implementation, let's take a quick look at the high-level design objectives. And these are kind of the standard design objectives for most isolation mechanisms. We want execution and data integrity for the host. The host in this case is the larger program within which we're trying to isolate a function call. This basically means that the host is protected from attacks originating in untrusted code. The second property is that each Vertine must be completely private and isolated from other Vertines, so it must not be affected by other running Vertines. And finally, we want strict isolation between the Vertine and the host, in that the Vertine cannot interact or read any data or any API calls outside itself, other than what may be explicitly permitted by the security policy in place. So what exactly is a Vertine? It is a lightweight isolated execution environment, and it is made up of three main components. The first one is a binary that has been generated by a modified toolchain such that it knows how to set up and invoke the correct isolation for the function calls you want to isolate. The second component is a hypervisor. So of course we'll need some kind of a hypervisor to isolate and run this function call inside. And finally, we have the host program, which is the larger program within which this Vertine is embedded. Note that this hypervisor can be fairly lightweight because it need not emulate the entire machine architecture. You don't need things like PCI or interrupts or even a lot of I/O. You just need enough capabilities to run a simple function because we're not trying to execute a full virtual machine inside it. Note that what exactly is a Vertine, or in other words, what is the function that you want to isolate, is currently determined by the programmer. And the way that is indicated is by a special new keyword in the source code. The authors took the LLVM-C compiler and modified it such that it recognizes this new keyword called Vertine. And when the compiler sees this, it will automatically generate code that will appropriately initialize a virtual execution environment and execute that function inside it. It takes care of other things such that the Vertine can get a view of the global environment within which it is executing. So for example, if you're accessing a global variable that is initialized to a snapshot at the time this Vertine is invoked. This diagram shows the overall high-level architecture. The Vertine hypervisor uses the kernel's KVM capabilities to set up an isolated environment to execute the Vertine. The Vertine hypervisor, which they call WASP, is responsible for doing that and for executing the untrusted code. So WASP is a fairly simple and lightweight hypervisor, and it benefits from the fact that it does not have to emulate the entire x86 platform. It does, however, have to mediate all interactions between the Vertine and its host program, and it does so via a hypercall interface, which is where it checks for things that are allowed by the policy. Now, even in the absence of needing to boot up a full kernel, that is, not having to emulate the entire machine architecture, we still need to do a number of things to set up the virtual execution environment. Things like set up the right paging tables, get into the right processor mode, and all of those things take about 35,000 cycles, which comes out to about 12 microseconds. One very important performance optimization is to have around a bunch of cached but uninitialized Vertines. As you can see in this diagram, you can have a Vertine in a state that is in the right processor mode, has all the right initialization done, and then snapshot it, which makes it really fast to then start up that Vertine when you're reusing it. So let's look at the performance of this, because it really does come down to how efficient and viable this mechanism actually is. Let's start by looking at the cost of initializing a Vertine. And over here on this graph, you can see that WASP, especially with caching, is faster than even initializing a thread. Like we saw earlier, it's on the order of tens of thousands of cycles. The next question is, what is the overhead at runtime after initialization? And here the authors have a pretty simple benchmark for a simple Fibonacci program. And you can see that as the computational intensity increases, in other words, as you do more computation inside the Vertine, the overhead becomes unnoticeable. However, for very short Vertines, there is a significant overhead, and that overhead is mostly coming from the cost of crossing isolation boundaries. That cost is about 5 microseconds for a Vertine, but it is almost an order of magnitude smaller for other mechanisms like VM run or doing a system call. So with this initial work and the evaluation and benchmarks that the authors have done, you can see that Vertines can be a viable and performant method to really push down the granularity of isolated execution down to the level of a function call. And that is a really interesting and unique and new point in the design space of virtualization techniques. This can have some very interesting potential applications, particularly for serverless functions, but also more traditional things like user-defined functions that are executed in databases. So that was a quick look at a new abstraction called Virtines that aim to execute individual function calls in an isolated virtualized environment. I hope you enjoyed that, and I will see you next time. Thank you very much.